It's an ambush involving sugars. All right. So we're going to start talking about solution chemistry and, for example, sugar and water, how they mix, how you can tell concentrations, all sorts of details about them. Now, when we look at solutions, solutions are a type of mixture, okay? And so a solution, like a cup of coffee with your sugar in it, this is going to be a homogeneous mixture. And those are called typically solutions. So solutions are just a type of homogeneous mixture, typically with some sort of solvent dissolving everything. Now, the solution is going to compose of two different things. You need to have at least one substance that will be the solute. This is going to be evenly dispersed throughout a second substance, which will be the solvent. The way you determine which is what do you have more. Okay? That's all that matters. Do I have more of the solvent? Yes, I always have more of the solvent. The solute, on the other hand, is the thing I have less of and is then dissolved in the other stuff. Okay? Okay. Your cup of coffee, by the way, has what solvent? What do you brew coffee with? Water. Water's your solvent, right? It's the thing you have the most of. Okay?
Unless you're at Starbucks.
Sugar. Yeah, cream. Maybe. Maybe. No, actually, cream could be your. Cream is a water-based solvent, anyways. But you could actually have cream as your solvent. Yeah. Or fat. Yeah. So you can actually do other things as your solvent. Now, the components in a solution do not need to react with each other. If they react with each other, you won't have those components at the end. And so then those would not be different compounds in your solution. So they need to not react with each other. If we were to take this coffee and we were to drink it, it would still be sweet. We would still be gaining sugars, right? And that's because the sugars don't react. They don't get destroyed. Sugar's still sugar. The coffee caffeine is still caffeine. The water is still water. Nothing's reacting. They're just dissolving into the water, and that's giving me my solution. Now, again, the solute is always substance that's in the smaller amount. For example, the coffee has several different solutes, actually quite a few if you, depending on what type of coffee you're having. But, for example, it has caffeine, that's one of the solutes. It has sugar, that's one of the solutes. It can have cream if you do cream, which is actually a whole bunch of things as well. So you probably have several hundred solutes in your typical cup of coffee. Okay. The solvent, on the other hand, is the thing you have the most of. It's the thing everything else is dispersed through. Okay. So that's going to be, in this case, water. You can theoretically have multiple solvents, but it's a very unusual situation, and you all will probably never experience that. Okay. All right. So, again, that cup of coffee, it's a dark brown color until you put the creamer in it. It's transparent. That's a big indicator to you that it's a solution. And when it's not transparent, that means there's things that are not actually dissolved in. Okay? So, for example, when you put creamer, anybody notice that the coloring changes a little bit, but also it's no longer clear, right? You can't see through it. And that's because creamer has things that don't actually dissolve in the water. Okay? If you were to let that sit there for long enough, you'd actually see the creamer settle out, which happens whenever I forget my coffee cup in my car. Yep. Seen that a few times. Whoops. So, once that sugar is dissolved in the water, it will not on-dissolve over time, as long as it's below the solubility point. Now, do note that you usually mix up coffee while it's hot, and so if it gets cold and you put enough sugar in it, you can start seeing sugar come. But that's because of the temperature difference. Okay. Now, these properties are a quick way to determine whether a substance is a solution. They're the guiding principles of knowing, do I have a solution or not? Okay. Did anybody notice I did not say anything about phases here at all? Yeah. So like I did have a liquid in this case, coffee, right? But I never said like you have to be this phase for this. Okay? And that's because you can actually make solutions of many different types of phases. In fact, you all have encountered many, many solutions that you didn't realize were solutions. Okay? All right, now, some of the things about solutions I have to remember from back in the day when we talked about mixtures, right, is they're homogeneous mixtures, right? And so particles need to be evenly distributed. If they're not evenly distributed, then that means that that's heterogeneous, isn't it? Okay? The components need to not chemically react with each other. If they chemically react with each other, then they're not going to be there for the solution, right? You'll have something else. In fact, they'll all react, and then you'll get something completely different. Okay. Aqueous solutions are typically going to be transparent because the water itself is transparent, and so when the things dissolve, they're almost always transparent. Now, don't forget, this could mean that if you have a dark enough dye, you could have trouble seeing through it. You have to put like a light right up against it to see through it, right? But that's still transparent, okay? It's just really, really dark, so all your colors go away. So keep that in mind. Like people get tricked out by that. Now the components, they don't separate upon standing. If you were to take your sugar water and just leave it sitting there for a month, it'd start growing stuff, but it wouldn't separate. Okay? You take your coffee and let it sit there for a month, it's not going to separate, right? You can leave it in your fridge, it'll still be coffee water. Okay? The concentration can be changed. So you can actually change your concentration. You could boil off some of the water, make it more concentrated sugar solution. A lot of people make like candies and stuff that way. And of course, you could increase the sugar concentration up to the solubility. So you could keep putting more and more sugar. Okay. You could also dilute it. You could put more water to dilute it down so it's not so sweet, right? All right, so the states of solutes and solvents. Now, solutions. These can be homogeneous mixtures of gases or solids. They can be any phases, realistically. That doesn't matter. So you can have gases and gases. You can have a gas into a liquid. You can have a gas into a solid. Do I need to do all the combinations? Thank goodness. All right. So we actually are very familiar, or like intimately familiar with solutions. They're all around you all the time. So air is a solution. It is primarily nitrogen gas. Okay? And that's actually your solvent. Your solute, on the other hand, is the oxygen you breathe. Okay? And so interestingly enough, our atmosphere is a nitrogen atmosphere. Anybody ever watch a sci-fi and they go, "You'll die out there, it's nitrogen atmosphere." All the time, right? They do that like every few years, this one that gets released, and they say that. What they mean is ammonia atmosphere. You die from that, not a nitrogen atmosphere. We have a nitrogen atmosphere. In fact, you would die the opposite way, or at least it'd be very flammable. The opposite way. If it was an oxygen atmosphere, like every time a spark happened near you, you just go boom. And you won't live very long. Nice sunny day, boom. All right.
Anything reflective.
Exactly. Your glasses on a nice sunny day, boom. Yeah, that's actually why, for example, the International Space Station has a mixture of oxygen. They don't use pure oxygen because any tiny spark from friction would set the place off. So, now, brass is another example of a solution. It's a solid, and you have a solute that is the metal zinc, and then the solvent is the metal copper. And so it's zinc and copper mixed together. Again, it's a homogeneous mixture, isn't it? And so brass is another solution. Okay. Anybody ever heard of orichalcum, by the way? No. If you ever play any video games or like fantasy stuff, it's a very common like magical mystical metal. Orichalcum is actually brass. Yeah, it's just the Greek name for a specific type of brass. So, yeah. Mystical brass. You've probably bought Orihelium and you didn't know it. You can go make your magical, sword or whatever. Now, again, solid, liquid, gas doesn't really matter. Solutions which the water is the solvent, these are referred to as aqueous solutions. Aqueous meaning water. So, water solutions, aqueous solutions. We see lots and lots of different solutions. Carbonated water is aqueous solution. When you open the cap, you're actually shifting your equilibrium and causing more of the gas to come out. And that's why it fizzes. But when you're just looking at it while the cap's on, that is going to be an aqueous solution where you're dissolving gas, which is the CO2, into the liquid water, right? And so we have lots and lots of examples of this. Whipped cream is a solution. You guys are kind of getting some of that. Yeah. Lots and lots of different ones. Now, there are some unique behaviors to water. Water is typically called sort of the universal solvent. It's the most common solvent on the planet. And most of the most important chemistries that we consider are water-based chemistries. And so each water molecule can form up to 4 hydrogen bonds with neighboring water molecules. Okay? And so you can get very complex networks of these hydrogen bonding. These are very strong attractive forces. And so this gives water some very unique properties not typically found in other solvents. One of the most interesting things for you probably is that the water has high specific heat. What this means is that water is a great trap for energy, okay? And can trap a tremendous amount of energy much longer than most other substances. Has anybody ever been to a coastal region? Okay. Much more moderate temperatures, right? So if you look at the Midwest of the United States, which has very little water in it and has a lot of distance from the coast, right? Did you guys know that they get hotter than the Sahara during the summer and they get colder than Siberia during the winter? Okay? And that's because the temperatures range tremendously in the Midwest. They can range 60 plus degrees in a single day. I've actually experienced a range of temperatures where it changed 160 degrees Fahrenheit in one day.
Where?
Wyoming.
Oh.
It started the day at 80, actually. It's actually a little more than that. And it ended the day at negative 80.
Ew.
Yeah.
No, thank you.
Yeah, it was pretty wild. So I showed up in shorts and a t-shirt and didn't have anything. This was like the summer too. This is the crazy part. It was like late summer. And I had football practice actually. And we were all out in our football practice gear, just regular t-shirts and stuff, and negative 80. And they finally canceled it after like 45 minutes of us freezing our butts off. Negative 80 at Wyoming is no joke, I'll tell you that. We have gusting winds of up to 120 miles per hour. It's hurricane level winds almost every day. Yeah. Okay, now the reason that happens in the Midwest is a lack of water. You go to the coast, you have these large bodies of water, right? So when it's hot, the sunlight gets trapped, the energy from the sunlight gets trapped in those water bodies. And then when it cools off, it radiates that heat back out. And so that's why you get these very small temperature differences when you're starting to talk about places that are next to the coast, right? They tend to be kind of the same temperature year round. Not a huge amount of difference. They go a little up during the summer, a little down during the winter, but not as much as like in the Midwest, right? Yeah. We don't have a huge number of water bodies here, but we're close enough that we get some of that coastal effect, plus we have some water bodies. Yeah. Running water doesn't do as good of a job. Now, water has a high boiling point and a low vapor pressure. In fact, most of the energy that's produced by the United States, or really any country, is actually used to heat and cool water. So that's actually the major use of energy. Ice floats on liquid water. This is actually because of a very unique property of water. This is very unusual. solid water actually has a lower density than liquid water. So when we have liquid water, it's not perfectly connected on every single hydrogen bond. Some of them are broken, about 20% of them are broken. And this actually lets the water molecules get closer together. When you have solid water, on the other hand, they have all of their hydrogen bonding in place. And so it actually causes the solid water crystals to actually expand. And you've all probably experienced this because, like, you put a water ball in the fridge, right? And then expanded and broke it, didn't it? Yeah. And water, solid water, is actually less dense as a solid than it is as a liquid. Okay? Very, very, very unique property of water. The vast majority of solids are more dense as a solid than they are as a liquid. Okay? That's very unusual. It's actually why a lot of the things happen, like icebergs happen, because the solid water is less dense. Your ice cubes float in your drink because they're less dense, right? When you make ice cubes, they actually like freeze from the outside, and then it causes little ice jets to jet out. That's why they have the weird like projections. Yeah. So, a lot of crazy stuff happening because of that. Now, colloids and suspensions. Now, this right here is a colloid. That's that creamer. Okay? It's not actually dissolved in the water. Okay? And that's why it's not transparent. So, milk and cream, they're not transparent liquids. They're not solutions. Right? There are parts of them that are solutions. If you ever like let milk sit in your fridge long enough, you see there's like a clear supernatant part, and then you get this cloudy part in the bottom. That's separating the colloid out. Okay? So, homogenized milk and cream, these are called colloids. Typically, to be complete, you can call them colloidal mixtures because they're mixed at that point. You've homogenized it, made it as homogeneous as you can. Anybody know what homogenized means, by the way? What they do? Okay, let me give you a little hint. Anybody ever like bought boutique honey or direct from the cow milk? Which is actually really difficult to do in the U.S. now, but yeah, they have flavors, right? And like it's different flavors. It doesn't taste always like the normal milk because they have flavoring depending on what they ate. And so homogenized milk is actually just taking milk from a bunch of sources and mixing it together. And so you get it homogenized, homogeneous, right? Otherwise, it would be heterogeneous, depending on the different cow. Okay? And different days. Yeah. And so these are going to have proteins, they're going to have fats. These are not actually dissolved in it. What they are is they're just, they can interact well enough with the water that they stay suspended for a period of time. Okay? And they will eventually fall out. Okay? So not actually dissolved. By definition, the particles in a colloid have to be between 1 and 100 nanometers in size, and that's why they'll eventually fall out. They're too big to actually dissolve in the water molecules. The water molecules are too small to support that weight. Okay? So particles of this size are going to remain suspended in solution. So a colloid does not separate over time if it is within a very narrow range of sizes. Anytime it gets bigger than that size, it's going to start falling out over time, okay, and separating. All right, now, these colloids and suspensions, these are a relative concept, okay? So like your solutions, they will never separate, period, ever. It's basically going to be impossible to cause them to separate just from sitting there. Okay. On the other hand, colloids and suspensions, you can get some separation and distribution of a colloid. A suspension is going to separate fairly quickly. Okay. Now, muddy water is an example of a suspension where it will actually separate fairly quickly. Okay. So if the diameter in the particles is greater than 1,000 nanometers, that's 1 micrometer, by the way, that's a suspension. That'd be like muddy water. You can actually see muddy water separate even over a course of like an hour or two, right? And so you can actually see those fall out fairly quickly. Okay. Blood is another suspension. You're probably really familiar with that one.
Mhm.
Blood cells being larger than 1 micrometer. That's why that's called microbiology. They're measured in micrometers. And they're going to settle out at the bottom of a test tube upon standing. So if you just left test tubes around in a fridge, you'd actually see them settle out. Blood can be separated pretty easily by a centrifuge. So if you put it in a centrifuge and spin it, you can actually cause those to separate very easily. And that's what they do in a lot of lab testing, actually. And that's the super named right there, your blood. These are your blood cells you get out here, along with a few other things that are fairly heavy. Okay? Okay. Now, a typical centrifuge will not easily separate out a colloid. So if you were to take a colloid and put it in the same centrifuge, what you would see is you may see a little gradient of it's a little more clear up here, it's a little bit more cloudy down here. But you wouldn't actually get a separation from this. Okay? If you got a powerful enough centrifuge, you could cause separation. Okay? But theoretically, if you got a powerful enough centrifuge, you could actually separate out solutions as well. Okay? Again, that would be an amazingly powerful one, though. Right? You guys know how you purify uranium? No? It's a giant centrifuge. Yeah. It's basically a centrifuge that would work on very, very dilute solutions of the two different forms you're trying to purify from each other. So it's a very kind of similar process. There's other ways you can purify uranium, but that's one of the main ways to do it in bulk and to get that final nuclear grade level. That's the place we bombed recently, by the way. We bombed their centrifuges. Yeah. You guys were aware of that? Yeah. Anyways, nobody's sure if we actually destroyed them or not, but it turns out we negotiated with them and everything turned out pretty decently, actually. Surprisingly so. That worked out ish. Ish. So let's remember our formation of solutions. So polar covalent compounds and ionic compounds will dissolve in water. This is because of that strong ion dipole attractions. Nonpolar covalent compounds are not soluble in polar molecules of water. That's the nonpolar versus polar, right? Or in this case, water specific, it would be hydrophobic, not dissolving in water, versus hydrophilic up here. Amphipathic molecules can interact with water with their polar portion, but these molecules typically do not form solutions because they have to assemble, so their polar portions are all facing out. Okay? So more often than not, most amphipathic molecules, at least the larger ones, do not form solutions. There are amphipathic molecules that can form solutions, though. This is, again, a general rule. Okay? For example, ethanol is amphipathic. Okay? That's the alcohol in beer. Now, the dissolving process requires individual solvent particles surround your solute molecules and interact with the attractive forces. This is what keeps them permanently suspended. They have to be the most stable state as being suspended. Okay? That process is actually called solvation for all solutes. More specifically, if it's an aqueous solution, this would be hydration. So solvation is the general one for all solutes in any solvent. Okay? But if it's an aqueous solution, that's hydration because it's water, as in like hydro, right? Okay, now let's talk about some of these factors affecting your solubilities in saturated solutions. Solution does not contain the maximum amount of solute that the solvent can hold. That's called unsaturated. And so you should see it all dissolved at some point. and it won't have any solid coming back out, that is unsaturated. If a solution contains all the solute it can possibly dissolve, then the solution is going to be saturated. So this is going to be, you've given it sufficient time, you've given it sufficient stirring, and you see solid still at the bottom. Okay? That's going to be saturated. So you've all probably done this with sugar at some point. I know they do this fairly commonly at the cafeteria with the iced tea, right? Where you have a little bit of sugar at the bottom, that's saturated. Okay? Okay. So, if more solute is added to a saturated solution, I'm teasing. I don't think they do that, actually. I think they actually do mix it pretty well. But you can do this, of course. This is like the case of the candies we were talking about being made. You heat water up, you dissolve a bunch of sugar in it, then you cool the water down, and you can cause the crystals to form of the sugar, right? Yeah. And so that's a saturated sugar solution. Now, the solute added to a saturated solution, your additional solute will remain non-dissolved, and it may not actually drift all the way down. So if you add crystals to it, you may lose track of them. What will happen is eventually those crystals will end up at the bottom, and they will be additional solid at the bottom. Okay? Because you cannot dissolve any more in a saturated solution. Solution that is saturated reaches physical equilibrium between the dissolved solute and undissolved solute. And so that state you're seeing in a saturated solution, that is its equilibrium state. Okay? It is fully saturated, it can't dissolve anymore, and it is formed in equilibrium. That's why I said that if you actually put solid in one of these, you may lose track of them, because the solid at the top could dissolve. But if it dissolves at the top, something at the bottom has to actually precipitate out. Okay? And so it may not be the same crystal at the bottom as it was that you put in, because it's in equilibrium. Now, at equilibrium, the rate of dissolving the solute and the rate of dissolved solute reforming crystals are going to be the same, and that's what the equilibrium arrow tells us. It's going to be a double arrow, and this is telling us that our reaction is going in both directions, and it's going at equal speed in both directions. Okay? So we get no overall change, but we constantly have some coming in, we have some going out. Okay? Has anybody been to like a really popular theme park or club? Those would be at equilibrium. You have the same number of people going in as you have coming out. Okay? And so your rate of difference is going to be the same. That is an equilibrium state. Okay, so this right here is an example of that. Again, we have this undissolved solute here. That's going to be an unsaturated solution where we have it all dissolving eventually. Okay? It can take a little while to dissolve, but it will all dissolve eventually. Right here, we actually have a saturated solution. See how there's solid letting out the bottom there? That's a big indicator that this is a saturated solution. And so what you're going to see is some of that solid is going to dissolve. Well, whatever dissolves has to come back out. Okay? And so you have some of it continuously dissolving, some of it continuously crystallizing, and this is going to always be exchanging back and forth. Your overall state, though, will not change. So if you were to watching this, you'd see spectacularly nothing. It'd be very boring. Okay? All right, let's talk a bit about some gout, kidney stones, and solubility. Gout and kidney stones actually happen when compounds exceed their solubility limits, and so they actually precipitate out in your body. Okay? Kidney stone precipitating out in the kidneys, obviously. The gout being typically like the feet being the big one. Gout is what Benjamin Franklin had. Yeah. So in the case of gout, the solid compound is actually uric acid. So in some individuals, the release of uric acid by the kidneys into the urine is actually reduced. This causes a buildup in the bodily fluids. What ends up happening eventually, if you get enough intake that would need to be converted, the insoluble needle-like crystals will form in your cartilage. It's extremely painful, very excruciating. and tendons at your joints. And this is usually at like the ankles and feet. And so the reason, for example, so this is usually a combined effect, by the way. Usually you have a genetic predisposition towards gout, and then you eat something that's very high in nitrogen, and you do a lot of that, and that sets it off. Once you form the crystals, they're actually very difficult not to continuously have problems with. Okay? And so from then on, you usually end up suffering from that from then on. It's very difficult to get rid of the crystals once they're formed, and once you have crystals, the new crystals tend to form very easily. Okay? And so, like Benjamin Franklin, likely his issue was actually the wine he was drinking, and a variety of different rich foods, which were very nitrogen rich. Okay, I actually knew a coworker that had a genetic predisposition towards this, and he got it set off by eating too much broccoli when he was trying to get healthy. When he was younger, he was like trying to actually compete in an event, and he was eating like broccoli and proteins every day, and it set his gout, and he ended up having gout from then on. Yeah. So it's one of those things that you can go without knowing you ever have a disposition towards it, and then if you get on the wrong diet, from then on, you just have to deal with it. Now, there are treatments that will dissolve the crystals nowadays, and so they can greatly reduce the effects on you, and in fact, even reset you if you're lucky. Okay? But there are treatments. Kidney stones, on the other hand, are going to contain uric acid. And what's going to happen here, they're going to have calcium phosphate, and they're going to have calcium oxalate. These are the three components that you typically would find in a kidney stone. They're going to form in your urinary tract, kidneys, ureter, or bladder. They can form in any of those. And these are going to remain, typically these compounds would remain dissolved in the urine. However, if your levels are too high, if you end up near saturation, because you're not removing them properly or you're building it up too fast, they can form a crystal then. Once crystals form, they are inevitably going to grow. Okay? You can reduce their growth, but they're inevitably going to end up growing. And so it's very difficult to get rid of those crystals. They end up insoluble. And eventually, hopefully, you pass it when it's still fairly small. Otherwise, they have to dissolve or powderize them with a combination of different chemicals or ultrasound. Okay? There's actually a few different treatments now for it. They've gotten better. So. Again, very painful. These are all very, very painful diseases. Hopefully, you never have to experience them. Now, the major way you can treat gout and kidney stones is actually changes in your diet and through drug therapy. So what you can do is if you limit the amount of uric acid you're building up, you can keep them from growing and, in fact, shrink them very slowly. Okay? Drug therapy can also help to dissolve them. You put something that will help break them up and dissolve them. You can also powderize them with ultrasound, but that's a little bit more extreme. And there's actually a whole series of treatments now that are specifically designed. So there's getting to be more and more kind of cool treatments for this. Now, let's talk about some solubility in terms of temperatures. Okay. Now, if we look at the solubilities of most solids, they're going to dissolve in water. It's going to increase with the temperature. So we talked about that with sugar water, right? You take sugar, you put it in hot water, you can dissolve it much faster, much more of it in the hot water, right? And so you're all probably most familiar with that, okay? We can actually manipulate this solubility by changing your temperatures. And I'd actually discuss that with making candy, right? So you get hot water, you dissolve lots of sugar in it, and then you cool that water down, and it's going to cause that sugar to start precipitating, right? And it does that because your solubility is going down, okay? Same thing happens with salt water. You can put a lot more salt when you're warm. When it's cold, it typically falls out more, though that is not as a large of a difference in solubility as you change temperature. Now, the solubility of a gas actually does the opposite. So, when you're looking at gas dissolving in water, like CO2 dissolving in water or O2 dissolving in water, gases actually become less soluble as you increase the temperature. So this is why, for example, the soda that I was getting rid of the carbon in, the carbon dioxide, you may have noticed that I had actually been heating that on a plate and stirring it so I could get rid of the carbon dioxide faster. Okay. You may notice that you can preserve your soda by putting it in the fridge, right? And it doesn't go flat as fast. Okay, that's because it's cooler. The gas is more soluble when it's cool. So when it's in the fridge and the cap's tightly sealed, your soda maintains that oversaturated state that comes from the factory. Okay. When you open your cap, and especially if you let it get hot first, anybody know what happens? It fizzes, right? That's because all the gas molecules are trying to escape. Okay? Because it is over its saturation. So the gas is all going to try coming out. Yes, this does mean, by the way, did anybody notice like fish populations are way bigger up north? Like near the poles? Yeah. That's because you have more O2 dissolved in the water. So they have an easier time breathing. It's one of the reasons you have these huge schools of fish. Not more fish life than you'd think. Now, this is Henry's law. This is the solubility and pressure. So, this is actually how they pressurize the sodas when they're at the factory. So, what they do at the factory is they take the soda can or the soda bottle, okay, and they have a little machine that is going to seal up the top there, and it's going to put it under tremendous pressure with lots of CO2. And so then they cap that immediately. And what you get then is a pressurized container. You may notice when you first get out of the vending machine, you can't like press down the sides easily. It's a lot more resistant. It's because it's pressurized. Okay. And so when you first open that brand new soda, it's typically cool and it's typically pressurized. And so you're going to break it open and it's going to go, right? Because it's releasing pressure. Okay. This process, by the way, was summarized by an English chemist. His name was William Henry. And this is that solubilities of a gas in a liquid is directly related to the pressure over the liquid. Okay? So the higher the pressure of the gas over the liquid, the more of it's going to end up dissolved in that liquid. And that's purely a factor of it being higher concentration over the liquid because of the pressure. And it's going to hit that liquid more often. When it escapes, it's going to have more of them come back in to replace this. If you have a lower pressure, on the other hand, you're going to have fewer molecules that can redissolve in that soda. So after you've opened your container and leave it open, you reduce the pressure on the outside, don't you? That would be this case right here. And what ends up happening in a relatively short period of time, within a day or so, it ends up flat, doesn't it? And that's because your gas molecules are going to escape, and you don't have this heightened pressure to fill it back up, do you? And so your equilibrium is going to equilibrize. You're going to get your equilibrium state, where you're just going to have the normal amount of CO2 in water that you would get for atmospheric pressure. Okay. Now, this relationship between gas solubility and pressure in Henry's law is actually how our lungs work as well. Okay, so this is how we have the gas exchange while breathing. So the pressure exerted by carbon dioxide produced in the tissues of the pressure of the oxygen inhaled in the lungs results in the exchange of the gas. The pressure of CO2 is going to be higher in your blood, delivered back to the lungs because it's higher concentration. Then the pressure of the CO2 found at the lungs, which would be the external atmospheric CO2. Okay? And so the gaseous CO2 is going to pass out of the bloodstream into the lungs. Oxygen is just going to be the exact reverse. So the pressure of the oxygen in our blood coming back to the lungs is much lower than the atmospheric CO2 pressure. And so what's going to end up happening is as long as we've taken in fresh O2 from our surroundings, that's then going to start dissolving into our blood. Okay? And then we have something to help us out. That's hemoglobin. And that's going to help us actually increase the amount that can then be fixed. Okay? It's going to buy us a little bit more time to be able to move that around. Going to let us go a little bit higher concentration. Not as much higher concentration you'd probably think, but a little bit. So the oxygenated blood then is going to circle through the body, and this just sums that up. So we inhale, and we're taking in fresh air, right? Okay. And so the atmosphere has a pressure of CO2 that's about 0.3 millimeters of mercury. Pressure of O2 is about 160 millimeters of mercury. The bloodstream, on the other hand, is going to have a pressure of O2 that's about 100 millimeters of mercury. And so we're going to get O2 dissolving into the blood. Okay. When we come back and we exhale, again, we're going to exhale, right? And so when we have the CO2, that pressure is about 40 millimeters of mercury. That's a lot higher than the 0.3, isn't it? And so a lot of this CO2 is going to come out into the atmosphere. It's going to escape, kind of like our Coke can before, right? And we're going to go, psh, which is our exhale, right? Okay, that's our psh. Yeah. And so we are then removing CO2 from our bloodstream. Okay, and we continuously do that all day, every day, lots of times, right? You stop doing it, you die. Because you build up CO2 and your O2 decreases. You need the O2 for your heart, brain to work. So. And all your cells work. All right. Anybody have any questions? Look at that. We got breathing down. That's an important one. All right. So ionic compounds. These are going to dissolve in water. If they completely dissolve in water, that's going to be a strong electrolyte. Okay. Soluble covalent compounds do not ionize, meaning they do not dissociate to form ions in water. And so these are called non-electrolytes. So for example, sugar in water is a non-electrolyte. Okay. If you were to take table salt, or you take like potassium iodide, or there's many others, these are going to be strong electrolytes. They fully dissociate in solution. And then ones that partially ionize in water, these are going to be weak electrolytes. Weak electrolyte meaning it does not come apart fully in water. Okay. Vinegar is going to be one example. Acetic acid, which is in vinegar, it's about 5% of vinegar. That is a weak electrolyte. Okay. But there's other examples as well. Anything that only partially ionizes, partially dissociates, is going to be a weak electrolyte. Okay, so there's an easy way to remember these names. First off, I have to discuss water. Okay? And so if I'm looking at water here, does anybody know, is water itself a good conductor of electricity? Do you get like pure water? Huh? Mm-hmm. So pure water is actually a poor conductor of electricity, interestingly enough. That's why you can actually use like water-cooled computers and stuff.
It's raining, and it, like, if there's electricity
it's not
down,
pure water. Yeah, so that's the secret. When you're experiencing rain, that is water with ions in it. In fact, you kind of knew that already because your windshield gets covered in that stuff whenever it rains on it, right?
I have no idea what you're talking about. What stuff?
Okay, so you experience rain, right?
Yeah.
And have you never noticed there's little trails of things that end up on your windshields?
Okay.
From the rain? Okay, those are actually salts that are dissolved in the rain. And then they're coming out on your windshield as it evaporates. Yeah. And so primarily those are like calcium salts, but they can also be sodiums. They're actually a mixture of things. And so pure water itself is actually a poor conductor of electricity. And so it's fairly resistant actually to conducting electricity. If you put non-electrolytes in it, it doesn't conduct electricity well either. Okay, that's why, for example, they use like basically windshield, your coolant in your car, something very similar to that. You can put that into like computers and stuff, and it will do a very poor job at conducting electricity. It's unless it dissolves ions, of course. So those are called non-electrolytes, literally meaning that electricity does not pass through water well, because it doesn't have ions. Okay? So if you were to put like sugar water and try to pass electricity to run a light bulb, it wouldn't light. Okay? All right, so what if we put something that's a weak electrolyte? This is actually vinegar water here. We've put a little acetic acid in it, which is a weak electrolyte, and you can see it lights up, but not very brightly, does it? Okay? Just a little bit. Right? And that's because most of this is not breaking apart. Most of it stays together and doesn't put ions into the water. Okay? Now, if you put a strong electrolyte like magnesium chloride here, the light bulb's going to light very brightly. And that's because those are all going to break apart, and it's going to cause the solution to have, well, it's a strong electrolyte, and it's going to have a lot of ions in it. Okay? And this is why we normally consider water to be a pretty good conductor, is because, well, it usually has a lot of strong electrolytes dissolved in it. It's very rare for us to find water that doesn't have anything dissolved in it. Yeah. And that's actually pretty difficult to do. As anybody that's ever put a water filtration system in their house knows, it's quite expensive. Yeah. Again, this is a strong electrolyte. When you put this in solution, it's going to dissolve essentially all of it into these ionic forms. Okay? Everybody kind of recognized that from when we talked about ionic compounds. When you put them into water, they're going to split up into their cation and anion, right? And that's going to give you your hydrated shells, like we had talked about before. And so this is a strong electrolyte. It is going to break up into its cation and anionic forms, and this is going to give you your dissolved salt. Okay. The solid magnesium chloride dissolves in water, yields me your magnesium and chloride ions. Now, remember that when they break up, you have to have the same number of magnesiums on both sides, the same number of chlorides on both sides, right? So when we dissolve this salt right here into water, we're going to end up with 1 magnesium and 2 chlorines, right? Which is going to be 3 ions that are dissolved in water from this. Okay? Now, remember, this is that law of conservation of mass. That's that French chemist, Lavoisier, that we talked about. That matter can be neither created nor destroyed. So whatever number of chlorides are in this magnesium chloride, we have to have the same number at the end, don't we? In this case, though, it's going to be broken up into the individual ions. Okay? Now, notice on this side, we have a charge of 0, don't we? So on this side, our overall charge has to be 0. Okay? Whatever charge you have on the reactant side, you have to have the same charge on the product side. Okay? So if we look here, we have a 2 plus and a 2 minus charge, don't we? And that gives us the same overall 0 charge. Okay. So we have to have the charge balanced. We have to have the masses balanced. And those two things always have to be true for any reaction. Okay. All right, so this is actually your charge balance right here with the math, in case you didn't understand where the 2 plus being and the 2 minus came from. All right, now, for ionic compounds, if we're dissolving an ionic compound in water, then that always has to dissolve as the ions. If it stays together, it won't dissolve. This would be a solid crystal here. So, whenever we dissolve an ionic compound, it always does what's called dissociation. Okay? It's going to come apart as its individual ions. Then the water molecules are going to surround it, like we talked about for the hydration, right? Okay, now, this reaction arrow pointing in one direction means this reaction is irreversible. You cannot go back. That's actually what tells you this is a strong electrolyte. So it being a strong electrolyte is it's irreversible, and so it stays as the ions and does not come back. Okay. All right, now, Substances like your solvent here, you may notice the solvent wasn't actually brought into this arrow portion, right? Because we don't actually care, like nothing's happening there. They're just spectators. They're not doing it. Okay? And so typically you go ahead and put them under your arrow, and those are conditions. We're doing this in water. Okay? This would be the same sort of reaction for a non-electrolyte. And so what we're seeing here is this is just going the same chemical compound, right? Sugar in this case. It's going from a solid in water. It's now aqueous, meaning it's dissolved in the water, right? Notice nothing changes about that compound other than the state, right? The phase. We have solid, we have aqueous. Okay. This is because these are all covalent bonds. They're not ionic bonds. So they're not going to break when you dissolve them. Okay? They're too strong. So again, solid to aqueous. Let's go ahead and look at weak electrolytes now. So this is actually the two functional groups we talked about a few times now, which is carboxylic acid and the amine one. Okay, these are very common to see in things that are weak electrolytes. Okay, they're very common to see whenever you're talking about acids and bases as well. So this is carboxylic acid, and this is carboxylate. Okay, notice this is the neutral form here. And then you lose an H+, and it gives you the carboxylate right here, which is the charged form. Okay. This one right here is the amine. You put it in something like water, it takes on an H+, and this gives you the protonated amine. Okay? Anybody had fish, by the way? Yeah. What do you do to make it smell less fishy? Take some like lemon, spray it over it, right? Okay, little spritz. Okay, what you're doing is the fishy smell from fish, those are amines. So if you put an acid, like a lemon, it protonates them, and it creates an ionic compound. Ionic compounds have lower vapor pressure, don't they? And so they don't smell as much fishy, because they don't have as much in the gas phase, right? You also get a more intense flavor, because it is soluble. You've made it more soluble, haven't you? Yeah, just like the drugs, right? Instead of HCl, you use lemon. And so that's why they always give you lemon whenever they're giving you like shellfish, or they give you fish in general. You can actually accomplish the same thing with things that smell fishy in general, because one of the fishy, like dead fishy smells, that's also because of amines. So if you spray them down with an acid, it will actually make it less fishy smelling. All right, now, carboxylate groups, these are going to contain a very polar OH bond, and so they typically are going to be very soluble. They can also dissociate to form the carboxylate ions, and your H plus ions when dissolved. And so this right here is going to be it dissolving in water, but also dissociating in water. Okay? And so what you're going to see is this is going to dissociate in water right here. See the double-sided arrow though? That tells you that it's going back and forth. Okay? That these will rejoin together to form this. It does not completely dissociate. It will only partially dissociate. Okay? Now again, if you were to add this carboxylic acid, this one's actually the one from vinegar, by the way, in case you're wondering. About 5% vinegar is this. It's what gives vinegar its flavor, and smell, and taste. Yeah. This right here is going to come apart. It'll form a little bit of it as the carboxylate with the positive H+. That's why it's carboxylic acid. It donates proton. And then these will come back together, and it'll form an equilibrium eventually. And so in your vinegar you buy, there's an equilibrium being established right there in your vinegar. And this is what it looks like. Okay. It's mostly this form right here. Very little of it goes to this. Okay, so the number of atoms and the total charge on each side has to be balanced. So the equation is always balanced. See how we have a negative and a positive over here? That gives you overall neutral viscosity. Okay. The phase of the weak electrolyte before hydration. This can be solid, liquid, or gas, or it can be aqueous. This typically would be aqueous. This is a very weird, strange way to write this out. This would be, writing it like this means you're taking pure acetic acid, putting it in water, and it's dissociating. Typically, this would be AQ right here for aqueous. And that'd be like vinegar. Okay. All right, now, ionic solutions and equivalents. Blood and other bodily fluids are going to contain many electrolytes as dissolved ions. It's actually an incredibly important part of our body's functioning, is that it's actually a pretty ionic environment. Okay. The amount of dissolved ions found in fluids, these can actually be expressed as a unit called the equivalent, EQs. You typically would see them if you're looking at like a blood report as like a milli equivalent. Okay. And equivalents are going to be relates to the charge in the solution, to the number of ions, or the moles of ions present. Easiest way to understand this is actually to look at some numbers. Okay. So like sodium has a charge of 1, right? And so sodium is going to be 1 equivalent for every mole of sodium because it just has a charge of 1. Okay. But if you have calcium 2+, this is going to have twice the number of equivalents per mole because 1 mole of calcium would be the same charge as 2 moles of sodium, right? Okay. And so chloride, for example, has a -1 charge. And so chloride, 1 mole of chloride, will be 1 equivalent. Sulfate, on the other hand, 2- charge. So 1 mole of sulfate would have 2 equivalents worth of sulfate. Okay. And what it does is it allows us to calculate up our net charge much easier, doesn't it? Okay. Okay, so let's look at some electrolytes in blood plasma. So again, the amounts of the electrolytes present in bodily fluids and typical intravenous fluid replacements are typically going to be represented by milliequivalents per liter of solution. And this is how you'd normally see them if you were looking at a report or if you're looking at IV bags or anything like that. So again, if we had sodium right here, this would have a concentration of 138 milliequivalents per liter. Okay. Right here we have potassium. It's 5 milliequivalents per liter. Here we have the magnesium 2+. It's going to be 3 milliequivalents per liter. Notice that moles would be half that number, right? Because it has a 2+ charge, it's counted twice as much. Okay, calcium 2+, 4 milliequivalents per liter. And so your total is 150, all of those add together for your positive ions. Okay. Now, when we look at the anions in a blood report, it typically should be the exact same total because you should have no overall charge. If you had an overall charge, you would be unstable. You'd attract one of the charges, right? And so this is the chloride. Everybody got the trend here. Anybody have any questions so far? This is actually interesting. This is proteins. This can be a bit variable. This is one of the major reasons this is always done in milliequivalents. Is because then we can figure these numbers out very easily because all we're looking for is charge. All right. Typically, blood plasma should have about 150 milliequivalents of cations and anions. And this would be a fairly normal range to see. This right here is some different IV solutions. So this is the normal saline that would be used to replace fluid loss in an IV bag. And this is just sodium chloride saline solution. It's 0.9%. Notice the milliequivalents per liter here. Same as your blood, right? So same as your blood plasma. This one right here is KCl with 5% dextrose, actually. So this one's actually used for a treatment of malnutrition and dehydration. And notice it's going to be a lower milliequivalence so that you can absorb water from it. Okay? Otherwise, if it was the same milliequivalence, you wouldn't be able to take water from it. It would just be a replacement for your blood plasma. You wouldn't be putting more water into you. Okay? Anyways, these are some different normal ones. An interesting side note to this is that a lot of these are actually sodium chloride, and that can cause blood pressures to raise when you give people them. The reason that you start seeing ones that have like potassium in here is because the potassium is actually what lets you regulate your sodium levels. So if you give somebody potassium and sodium together, the blood pressure won't raise. The other part that's kind of interesting, a lot of these are normally like you'll see ones that they use sugar-based solutions to deliver drugs, and it can really cause havoc with people with like diabetes. So I actually had to bring that up with a drug that they were giving to my mother. Her diabetes kept getting set off by it. I'm like, what are you guys using for your IV bags? Yeah, it's sugar. Yeah. Not like that's going to affect anything, huh? The amount of solute dissolved in the solution is going to determine its concentration. There's numerous ways of calculating concentrations. So the concentration of the solution is going to be expressed in a variety of different units, but overall concentrations are the amount of a solute you're discussing. So like we had talked about sodium chloride in some of these, sugar in some of these, etc., right? Recently, we're doing a lab where we do sugar, right? Concentrations of sugars. This is going to be divided by some amount of your solution. Okay, your overall solution amount. Now, the denominator here is the total amount of solution. This will include the solute. It's not just the amount of the solvent. It's not just water. Okay? All right, so this one right here is kind of an interesting one. This is very commonly used by chemists, but you don't see this used by a lot of other people. And so this one here is millimoles per liter or molarity. So the units for electrolytes are sometimes given as millimoles per liter instead of milliequivalents per liter. Note that milliequivalents and millimoles are actually tightly related, aren't they? Milliequivalents is just with the charge included. Okay? And that's because a lot of these tests were originally conducted by and determined by chemists. So, yeah, we like our molarity. We really like it because it has moles. Yeah, makes it easy to do calculations, right? Now,
convenient for molding.
It is very convenient for mold day. By the way, mold day is today. Don't forget, folks. Okay, so the charge on your ion is going to be the number of equivalents present in 1 mole. So for sodium, it's going to be the number of equivalents equal to the number of moles. For calcium, it would be 2 plus. So right here, this is molarity. If you guys want me to, I can scar it into your mind so you'll never forget. I did that to my friend in college by accident. We were studying late one night. We'd both way too much coffee, like 6 pots of coffee at that point. And he was having so much trouble remembering what molarity is, which is moles over liters. So moles of solute over liters of solution. And he was having a lot of trouble with the exams. And so, like, it was the 20th time. It was 4 a.m. And I just went, damn it, it's moles over liters. And I yelled it so loud that we were on the 5th floor of a building, and the security came in from outside. Like, I have lungs on me. You guys haven't experienced it, but I've actually shouted so loud in a football game because people are like, you gotta cheer louder, blah, 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 that I stopped everyone from cheering, and they all looked at me. Yeah. I went, fine. And It's funny because 10 years later, he is PA up in and he's sleeping next to his now wife, and he like wakes up like moves over leaders. So apparently, I scarred it into him permanently. Okay, he's never forgotten. So, if you need me to do that for you, we can do it. I don't quite have the lungs I used to, but now millimoles per liter is the same as the millimoles of solute over liters of solution. Notice that this is just another way of representing this, so you can talk about smaller amounts that are 1,000th of a molarity. This would be a millimolar, in case you're wondering. Okay, millimolarity. Okay, this is the steps to calculate these. So you examine your problem, decide what information is given, what information is being sought. Notice it's again, what do I have? What do I need? How do I get there, right? Okay, so percent concentration. We've actually used percent concentration in the lab now. Notice that this is also something that you've probably seen around a lot too. Like if you ever were to look at the alcohol content on a bottle, this is what it's in. Okay. Now, this is going to be a percentage, so it's out of 100, right? So it's going to be parts of the whole times 100. So parts of solute divided by parts of solution, so your total amount, right? Times 100 to get in percentage. Okay? And that's all percent is. Now, note that there are actually a few different types of percentages. Okay, you may have seen them before. There is percent V over V, percent W over V typically, and then percent W over W. Okay, and so what those are is you can have percent mass over mass or weight over weight. Okay, this is going to be percent, and you'll have some sort of M over M, WT over WT, W over W sometimes. And what it is you've taken the mass, grams of solute, divided by the mass of the solution, times 100%. Okay? It's typically the easiest one to do in labs because we have mass measurements that's very easy to do. Percent V over V. So this is just going to be volumes over volumes. Okay? So you do the milliliters of your solute over the milliliters of your solution. Okay? Note that it doesn't matter if you do like liters over liters, that also would give you the exact same number. Okay? All right, now M over V. This one's a little bit less usual. It's usually used when you have like a solid and you're dissolving it. So then you can measure out your solid mass, throw it in there, dissolve it, and measure out the volume. Okay? But this is going to be M over V. You're going to have grams of solute over milliliters of solution. Not pretty oftentimes used for intravenous fluids because they take solid, measure it out, and throw it into a liquid, and then fill it up to a certain volume. Okay, and so that's very easy to calculate for that. You can also call it W over V. That's fairly often seen when they don't put M over V. So let's talk about this as compared to some different common units. So for example, the unit used for measuring oxygen carrying protein hemoglobin in blood is grams over deciliters. Notice it looks like that, doesn't it? Yeah, that was the percent mass over volume. We're just using deciliters there. Okay. The range for men would be 13 to 18 grams per deciliter. The range for women is typically somewhere around 12 to 16 grams per deciliter. And those would be considered normal levels for your hemoglobin content in your blood. I guess we're done. We're out of time. You all have a wonderful day.